Welcome everyone. Today we have Sara Ahmadian from University of Waterloo. Sara is expert in clustering and facility location problems, and she's going to tell more about our exciting recent work.
Thanks for the introduction, and thanks everyone for coming. So today I'm going to talk about clustering and facility location problems. So first I'm going to give you an introduction to what these problems are, then I will mainly focus on the k-means clustering problem, and at the end I will give you some future direction. So facility location problems, there are fundamental problems studied in operation research and theoretical computer science. They have lots of application in data mining, image processing, and information retrieval. Many economical decision problems concern selecting or placing facilities in order to serve a given set of demands efficiently. And examples are when we want to set up manufacturing plants, distribution centers, hospital, fire station, etc. Many of the facility location problems are NP hard. And so for these problems, we design approximation algorithms. So let me give you an example, a more concrete example on facility location problems. So suppose that you want to set up servers in a network for some certain application. Setting a server at a host incurs some overhead, traffic, maintenance cost, and there are some clients that you want to service. So every client demands to access its data from the closest possible server in order to minimize its delay. So the optimization problem here is where should we set up the servers in order to minimize the total installation costs of the servers along with the propagation delays. So let me give you a formal definition of the problem. In this problem, we are given a set F of facilities, and each facility has an opening cost. Each facility I has opening cost Fi. We are given a set D, a set D of clients, and these facilities and clients are located in a metric. We have cost Cij that denotes the connection cost or assignment cost of client J to facility I. And I will use J to index the clients and I to index the facilities throughout the talk. So the goal here is to open a set S of facilities and find an assignment of clients to this set of facilities. And we want to minimize the total cost of facility openings, so the sum of FIs, plus the total cost of connection, the total connection cost of clients. So we connect each client to the corresponding facility, and then we want to minimize the total cost. And without loss of generality, we can assume that a solution is characterized by just a set of open facilities, because we can just assign each client to the closest possible facility. So we can really remove the assignment part, and then we use the notation CJS to denote the costs of connecting client J to the set S. So now let me give you an example here. Suppose that we have a set of facilities F, and facilities are shown in the picture by red squares. Each facility has opening cost 10. We have a set of clients D. They are shown by blue circles. And they are located in a Euclidean metric. And we want to find a set of facilities to open such that we minimize the total cost of set S. And so, for example, if we open these three facilities, and then we assign each client to the closest facility, the cost for this set will be the facility opening cost plus the client assignment cost. So we opened 3 facilities. So in total, we are going to pay 30 for the facility open costs. And then these are in Euclidean metrics. So whatever distance that is from this client to that facility will be added to the cost. So I've done some work on facility location problems. I worked on lower bounded facility location problem, mobile facility location problem, and minimum load K facility location problem. There are some approximation algorithm results for these problems. And this was in the beginning of my PhD. Then I moved toward working on clustering problems. So clustering problems are basically captured by facility location problems. And in these problems, we are given a set of data points, and we want to partition the data set into clusters such that the data in each cluster, they share some common trait. So basically, the data in each cluster, they are kind of close to each other with respect to some distance measure. And clustering is a form of unsupervised learning because in the beginning, we don't have an example that shows us how this clustering should be done. And it's also a method of data exploration because we can use it as a way to look for patterns or structure in the data. So why do we consider clustering problems? There are various reasons for this. One reason is we want to organize data into clusters to show some structure in the data. For example, we cluster genes to do that. Or sometimes the partitioning itself is the goal. So for example, in market segmentation, we cluster the clients so we can have a targeted advertising, which is more effective. And it can be because we want to prefer for some other AI techniques. So we want to summarize news. We cluster the news, and then we find a centroid for this news. Or it might be because we just want to do some discovery in the data. So we want to find some underlying rules or some recurring patterns or topics in the data. So now let me give you a formal definition of the clustering problem. So in this problem, we are given a bound K. We are given a set D of clients. And these clients, they are located in a metric C. So we use a Cij to denote the cost of assigning client J to facility or center I. So now the goal is to find a set S of clients that will be our centers. And this set should have a size at most K, such that some objective function is minimized. So depending on what your clustering problem is modeling, you can have different objective functions for measuring the quality of your solution. But the most famous objective functions that have been studied are K-center, K-median, and K-means. So for example, in K-median, we want to minimize the total connection cost of client J to set S. So just the sum of the connection costs. Another famous clustering problem is a K-means problem. I've done a project on this problem with a group of people at EPFL, Ola Svensson, Justin Ward, and Ashkan Nurzifar. So this result is a recent result, and it was published in Fox 2017. And so let me first give you the definition of K-means problem. So there's a generic definition for the K-means problem. And it says that we are given a set of points D, which is x1 to xn, so a set of n points in Rd. And we want to find a set S of K cluster centers in Rd. In this definition, the set of points or the set of centers can be arbitrary, so it can be any point in Rd. And we want to minimize the sum of squared Euclidean distances of clients to this set S. We can also give a facility location definition for K-means problem. So in this definition, we say that we are given a bound K. We are given a set F of facilities. We are given a set D of clients. And they are located in some metric, so it's Euclidean metric. And we want to find a set S of facilities of size K and assign clients to this set. So we want to minimize the total sum of squared Euclidean distance of clients to this set. So our algorithm is going to work with this definition, but this can be assumed with a loss of generality because even if we are given the first definition, by losing a small factor in the approximation ratio, we can build an instance that is consistent with the second definition. So we can assume that we have the second definition.
Actually, how much you lose in approximation?
It's just an epsilon factor.
So does your algorithm work for non-Euclidean metric, for general metric? So it really uses Euclidean structure somehow?
So our algorithm works for both, but we get different approximation ratio.
Somehow, in Euclidean case, you get something better.
Yes, because we have more, we have better inequalities. So the most commonly used algorithm for k-means problem is the Lloyd's algorithm. In theory, there's no worst case guarantee for Lloyd's algorithm, and the algorithm may not even converge in polynomial time. But in practice, the speed and simplicity of the Lloyd's algorithm cannot be beat. And Arthur and Wasilewski proposed a randomized initialization step for the Lloyd's algorithm. So they got a new algorithm, k-mean plus plus, where for k-mean plus plus, now we can say that we have theta log A expected approximation guarantee. And Ostrovsky et al., they show that if the data set is clusterable, then the Lloyd's algorithm is actually a p-test, so polynomial time approximation scheme, which means that it finds a solution that has a cost very close to the optimal cost. And clusterable here, it means that when you look at your data set, you have k well-separated clusters on the data set. So some related work on k-means problem. The previous best and only approximation known for this problem was by Canningo et al., which was a local search-based algorithm. It had 9 approximation guarantee, and they show that the analysis is tight. So the local search cannot do better than 9. And although the general problem resisted improvements, in some special cases, there's been some progress. So we get p-test in a special case that the k is constant or the dimension is constant. And actually, for the constant dimension, these two independent results, they both show that the same local search that gives 9 approximation, it gives a p-test if the dimension is fixed, constant. So now that we know that local search cannot do better than 9, and we know that LP-based methods, they have been very successful for facility location problems. The question is, can the LP-based algorithm do better for k-means? And LP-based algorithm, they give nearly tight understanding of uncapacitated facility location problem that I introduced, and they 1.488 approximation, which is close to the lower bound for this problem, so the hardness for this problem. And they give 2.675 for the k-median. So we worked on this research problem, and we answered this problem positively. So we find an LP-based algorithm for k-means problem. The algorithm, the core of the algorithm is really Jain-Vazirani algorithm for the k-median. And our result significantly narrows the best known upper bound and the lower bound. And it works for the general k and general dimension. So we get the following result, that we get 6.35 approximation for k-means problem. And we show that the integrality gap of the LP is at most 6.35. So this is for the facility location problem in Euclidean space. And we have some results for other problems. For Euclidean k-median, we get 2.633 approximation, which improves a little bit the result of Birka, but actually that result is more general because it's in general metric. And for k-means in general metric, we get 9 approximation, and we show that the integrality gap of the LP is at most 9. So I should mention that the integrality gap of the LP is the ratio, the maximum ratio between the cost of the integer solution of the LP and a fractional solution of an LP. So we show that this gap is, integrality gap is at most 9. The previous result was 16 approximation by Gupta. And for this version of the problem is 3.94 hard to approximate. So as I mentioned, the core of our algorithm is really Jain and Vazirani algorithm for k-median. So I'm going to go over this algorithm and give an overview what this algorithm is and then say how we make improvements. So Jain and Vazirani algorithm is they have a primal dual algorithm for k-median problem. So we are going to focus on k-median problem at the moment, and then I will tell you when we switch to k-means. So we just want to minimize the total cost of connection cost of clients to a set of open facilities. So in a primal dual algorithm, we have a primal LP and we have a dual LP. We are not going to solve the primal explicitly, but what the algorithm do is that it will create a feasible primal solution while creating a feasible dual solution. And then this dual solution is used as some sort of certificate to prove the bound on the cost of the constructed feasible primal solution. So there are 2 main steps in the algorithm: the primal dual step and the combination step. And then the primal dual step consists of 2 phases. The first phase is dual growth phase, and the second phase is pruning phase. And really, the first step of the algorithm is focused on solving the facility version of the k-median problem with uniform facility opening cost. So we are going to remove the bound k on this set of open facilities, and then we pay a uniform cost for opening a facility. And then the second part of algorithm is really focused on finding an appropriate opening cost that for that opening cost, the algorithm opens close to k locations. Okay? So let's see the LP formulation for k-median. We have this LP formulation, and we have 2 variables in this formulation. One variable is yi, which is an indicator variable that shows that if a facility I is open or not. And then we have an indicator variable xij, which indicates whether client j is assigned to facility I. And in the LP, we want to minimize the total sum of the connection cost of clients to facilities. We want each client to be assigned to some facility. If a client J is assigned to facility I, we want that facility to be open, and we want to open k facilities in total. So, as I said, we are going to look at the facility location version of this problem. So we are going to remove this inequality, and instead we add a multiple of a gamma factor, or a gamma multiple of this inequality in the objective function. So it means, so now if you look at this, it's basically saying that for every open facility, pay opening cost of lambda. And then we are deducting minus k lambda, which is for a fixed lambda, it would be a constant factor. So you can just ignore it. Okay, So we have this LP, and we are going to denote it by LP of lambda. And we get this dual for the LP. So in the dual, we have two variables. One is alpha j, and one is beta ij. They can be interpreted as follows. So we have alpha j variable, which basically says what is the budget of client j. And we have beta ij variable, which says that what is the contribution of client j toward opening cost of facility I. And now, if you look at the dual, we are maximizing the sum of the budget of the client. This is just a constant term, so you can ignore it. And then this inequality basically says a budget of client j can be used for paying the connection cost of the client plus the contribution of client j toward opening cost of facility I. And the second inequality says we want the total contribution of clients toward facility I to be at most the opening cost of facility I, which is lambda. Okay? So, as I said, now I'm going to explain this first step of Jain and Vazirani algorithm. So the primal dual step, that we want to solve a facility version of the k-median problem where the facility opening costs are uniform. Okay, so this step consists of two phases. First phase is dual growth phase, in which we will construct a feasible dual solution alpha and beta to the dual of the LP. And then in the pruning phase, we construct a feasible solution of the primal LP. And we try to bound the cost of this feasible solution with some multiple of the sum of alpha j's of the dual solution that we constructed in the dual growth phase. Okay? So the dual growth phase is as follows. We are going to start with the feasible dual solution 0, 0 to this dual. And we always have a feasible dual solution. Excuse me. So I'm going to explain the algorithm using a picture. And the algorithm starts with 0 dual solutions, and we uniformly increase the dual variable of all active clients. So in the beginning, all the clients are active. So we have 4 clients, different colors, and we have 4 facilities. I'm going to use this bar to keep track of the contribution of clients toward the opening cost of facility. So basically making sure that this inequality is feasible. And then we are going to increase the alpha j of clients. So this would be like we have a ball or a circle around each client, and we are increasing this ball. So the radius of this ball would be alpha j, and we are increasing this alpha j. Okay, so we start increasing the alpha j of all clients at a uniform rate. So we increase it until, say, a client becomes, its alpha j is enough to reach a facility, which means that this inequality becomes tight. So alpha j becomes equal to Cij for this red client and this facility I. So if this happens, we start contributing toward the opening cost of a facility. Okay, so red starts contributing toward the opening cost of this facility, and later on toward the opening cost of this facility. And we continue this until for some facilities, they become tight or they become fully paid, which means that the contribution of clients toward these facilities is enough for opening this facility. So basically, this inequality becomes tight. So this means that we are going to say these facilities are tight, and any client that can reach these facilities, we cannot increase their alpha j anymore, because we want to have a feasible dual solution. So these clients, they will become inactive. So for example, blue and red client, they will become inactive now. And then we continue the algorithm until all the clients become inactive. So in the next step, this facility becomes tight, and then these two clients are contributing toward it, so they stop increasing. And then everything becomes inactive. So this concludes the first phase of the algorithm. So we constructed a feasible dual solution. So now we are going to construct to a pruning phase, that we want to construct a feasible facility location.
So the beta ij's, how does it contribute? It's just the value of alpha j when it hits the facility.
The beta ij is how much client j contributes toward facility I. So if, for example, if you look at this red client, we have alpha j. So alpha j, the budget of client j, is going to be used for reaching this facility, Cij, and then beta ij would be the difference between these two. So this beta ij would be basically alpha j minus Cij. So if you look at the picture, it's kind of like this part, because this is Cij, then this would be alpha j minus Cij. Okay. So yeah, good question. So this is how we construct a feasible dual solution. And then in the pruning phase, we are going to construct a feasible primal solution. So we have these tight facilities, and we are just going to pick some facilities to open from these tight facilities. Okay, so facility 1, 2, 3 are tight. 4 is not tight, so we ignore it. So in order to decide which facilities to open, we are going to construct a graph H on the set of tight facilities, which I denote by Ft. And then we put an edge between two facilities, I and I prime, if there exists a client that makes a contribution toward opening of these two facilities. This should be strictly bigger than 0, so makes a contribution towards opening both of them. So for example, if you look at facility 1 and 2, red client is contributing toward opening both of them. So we are going to put an edge between these two facilities. And then we are going to pick a maximal independent set between tight facilities. The reason we pick an independent set is that we want to have the property that each client contributes toward opening of at most one facility. Okay, so that's why we pick a maximal independent set. So say we pick facility 1 and 3 to open. So we decided what facilities we want to open. The next step is decide how to assign the clients. So if a client using its alpha j can reach a facility, which means that there exists some facility inside its ball, then we assign that client to that facility. Okay? And then if there's a client that no facility from its ball is selected, we know that this client stopped at some point, so we know that there's at least one facility inside its ball that it's tight. It wasn't picked because it had some edge to some other facility in this graph. Otherwise, we should have picked this facility in the independent set. So 2 wasn't picked because of this. We picked facility 1, so we are going to assign this blue client to facility 1. Okay, so now we constructed a feasible primal solution. So the next step is really bounding the cost of this solution. So let's first bound the connection cost of blue client to facility 1. We have triangle inequality, so we can bound the cost of this blue arrow by these 3 parts. And actually, it can be shown that each of these segments, they are at most alpha j. So we can say that the distance of this client to this facility is at most 3 times the alpha j or alpha of this client. Okay? And so now let's do the analysis.
So why is it, see why the first ball must be alpha j?
Uh-huh.
Why must the other ball also be alpha j for the blue one?
So the idea is the following. So this red client is making a contribution toward this facility, right? So, and then this blue client stopped increasing its alpha j when this one became open. Okay? So it means that this red one also stopped contributing toward 2 at the point that this one stopped. Okay? And now the reason this one its alpha j can be bound is, first of all, it was stopped by the time this client stopped. So it means that this alpha j cannot be more than that. And it's also possible that it's even stopped before that. And so you can say this is at most alpha j, and then this is also, it was stopped because of this facility, so that distance is also at most alpha of that one, which is bounded by the alpha of this one. So for each client, we can say one of the 2 following things. Either the alpha j of client can pay for the contribution for opening some facility I for contribution toward opening facility I plus the connection cost of client to that facility. For example, orange, green, and red client, they have this property that their alpha j can cover their contribution plus their connection cost. Or you can say that the alpha j can pay for 1/3 of the connection cost of the client. So this is the case for the clients that are not directly assigned. And now if we sum this up, since the set of facilities that we decided to open are independent set and fully paid, if we sum all this up, we get that we can pay the cost of opening all the facilities in S plus 1/3 of cost of clients to the facility S can be bounded by the sum of alpha j's. So I know this got a little bit technical, but what I want you to remember from this part is the following, that if the primal dual algorithm returns a solution that opens exactly K facilities, then the connection cost of clients to this set is at most 3 times the opt of K median. Okay? So now we can move to the second part. So in the first part, we design an algorithm that works for arbitrary opening cost lambda. And now we are going to the second part, that we look for an appropriate lambda. So the idea here is that if the lambda is small, so the facilities are cheap, a facility location solution is going to open a lot of facilities. And then if lambda is large, so facilities are expensive, the solution is going to open a few facilities. So now, by appropriating selecting lambda, we can expect the JV algorithm to open close to K facilities. But really, we cannot guarantee that we find this lambda, but we are saying that we can find some lambda that opens close to K facilities. And so a binary search step is done in this step, and I'm not going to go through the details of that, but the idea is that the binary search step is done, and then losing a factor of 2, a solution of size K is found, size at most K. So Jaina-Vazirani algorithm for K median gives 6 approximation. Okay? So now, if we try to use the same algorithm for K means, so just instead of having the Cij in the LP, we will have Cij squared in the LP, so the square of Euclidean distance. If we use the same algorithm for K means, in the first step, we are going to get 9 approximation. Why? So you remember this case that we had client J and it had to go like a 3-hop thing to get assigned to facility I. Its alpha j is 1, and then its distance to I was 3. So we had 3 approximation for k-median. But now remember that we are in a k-means problem now. So the alpha j of this client is 1, its distance to its facility is 1, but then if it does 3 steps, then we will have 3 to the power of 2, so 9. The distance is really 9. So we get 9 approximation here. And then doing the same combination step as Jain and Vazirani, we lose a factor 4 here. So in total, we will get 36 approximation.
So actually, I have a question. So these LP-based algorithms, are they known to give better approximation for all clusterable instances? So you said this about k-means plus plus, but or Lloyd's algorithm, whatever. But
yeah. I mean, the only LP-based algorithm for k-means is our algorithm, and
well, I mean, also Jain Vazirani gives something, right? It's not.
No, but you said in the case of clusterable, right?
Yes.
Assumption. So I mean, we don't use that in our analysis. Maybe if you use that, you can get a better approximation.
But do you think it's possible or not? And maybe ideally, like one.
Actually, yeah, it might be possible. Yeah.
In fact, I think there is some work by Kostya
Like
and others.
bunch of well-separated clusters.
Well separated.
Yeah.
In terms of distance.
In terms of distance.
Yeah, in fact, there are some work on that actually. It gives a p-test,
I see.
like just solving the LP.
I see. Okay. No, that's very
Yeah.
natural.
Okay.
I don't know which k-means, or I don't know which combination, but there is.
No, but pitas are equivalent, right? Because
Yeah,
you're just
right.
losing constants.
Yeah, absolutely.
1+.
So yeah, so this gives 36 approximation. So now what are our improvements? So here in our algorithm, there are 2 main things that yield the improvement. First of all, we have a relaxed pruning phase, which enables us to get 6.35 approximation in the first part. And then in the second step, we do something completely different from binary search algorithm, and then we don't lose any factor here. So we get 6.35 approximation for k-means. Okay? So now let me explain the relaxed pruning phase. So you remember the bad... Yeah.
Before you go on, combination phase where you don't lose anything, does this trick also work for k-median?
Yeah, I mean Euclidean k-median.
Euclidean. So that's how you get an improvement there?
Yes. And so you remember the worst case was this case. So this case happened because we had this client J was contributing toward opening of I and I prime. And we didn't want to open I and I prime at the same time, right? So, but the idea is that for this client J, we know that the alpha J is equal to beta ij plus Cij squared. So for this facility I. But in the analysis, what we really use is the beta ij plus 1/9 of Cij squared for the 9 approximation. So really, we have 8/9 Cij squared slack here. And then maybe we can use this slack for opening facility I prime. Okay? And then the reason we got really bad approximation was that really these are on a line and these facilities are far. If I was a little bit closer, we wouldn't get 9. So these facilities are really far, and they are kind of very far from J as well. So the contribution of J toward opening of these facilities are really small. So maybe we can do something here. Okay, so what we are going to do is that when we construct the graph, H on the tight facilities, we put an edge between facility I and I prime if there's a client that contributes toward opening both of them and the facilities are close. So I'm not going to define what exactly close mean, but it's related to the alpha J of the clients that contribute toward the opening of facility I. And in this case, these 2 facilities are really far. Okay? So this new graph, it has less number of edges, so it's more sparse, right? And then we have a relax. That's why we call it relaxed pruning. And now the idea is that in the new analysis, when we pick an independent set, it doesn't necessarily mean that each client is contributing toward opening of at most one facility. Okay, because it's possible that there's no edge between two facilities, but there's a client that contributes over both of these facilities. But the idea is that if a client contributes toward opening of more than one facility in the S, we know that the facilities are far. Okay, and then we show that the alpha J of the client can still pay for a fraction of the connection cost plus the contribution toward all the facilities that are opened in S. Okay? So now, and then with this new pruning phase, really the worst case that can happen is something like this. So if I didn't open this facility, it's because of a facility that is kind of close. So this facility cannot be really in this area. It has to be closer. And now I get 1 plus square root 2, 3 to the power of 2 approximation, which gives us this 6.35. Okay? So this is how we get improvement in the first part. And then the combination step that I said we do totally in a different way. So our combination step, we examine the various opening costs sequentially. So we first look at the lambda 0 equal to 0, then lambda 1 equal to 1, lambda 2 equal to 2 epsilon, lambda 1 equal to epsilon, and so on. And then when we want, the algorithm stops for the first lambda L, that the size of independent sets becomes smaller than K. When we want to construct the alpha dual solution for opening cost lambda L plus 1, we use the alpha of the previous round. We start from that and we increase that one. And the idea here is that we get two solutions, alpha L and alpha L plus 1, that are kind of close. So if you look at their L infinity difference, it's at most 1 over n squared. So they are really close. And this means that if a facility is tight with respect to one of the alpha L's, since the opening costs are also close, we can say that the facility is almost tight with respect to the other alpha. So a facility is tight in one solution, in the next solution it will be almost tight. Okay? So the way we construct the independent set is also we do it sequentially. So when we are at the graph HL plus 1 for the L plus 1 round, we start with the graph, we use the graph of the previous round. So suppose that we have K equal 3, and then at the previous round, the independent set has size 4. Now we want to construct the independent set for this round. So what we are going to do is that we construct a hybrid graph H from the union of these two graphs. And we also add these edges between the facilities of one solution corresponding to HL and facilities of the current round. So I use prime to denote the same facility but a new copy. And then we put an edge between two facilities if there exists a client that makes a contribution in one solution, in the first solution, and then in the current solution that we are constructing. And again, if the facilities are close. Okay? So the goal is to construct an independent set for this graph. So we start from the independent set of the top graph, and then first we expand it to a maximal independent set. And we are going to remove the vertices of the HL one by one until we get the current graph. So we remove the vertices one by one and update the maximal independent set. So when we remove this one, we need to update the maximal independent set, and then we continue until we get to the current graph. And now the idea is that K is equal to 3, and now the size is 2. So if the size goes below K, we know that at some point by the way we've done the updates, the size of independent set can decrease by at most 1. So if I go below k, there was a point that I had an independent set of size exactly k. So say at this point. Now remember that we had this idea that the alphas are closed. So these two facilities are tight with respect to alpha L plus 1. And this is almost tight with respect to alpha L plus 1. And now, so we return this solution has the size exactly k. So that's why we are not going to lose a factor. It's just we use a factor epsilon because this facility is not tight. So we lose an epsilon factor in the approximation. But we found this solution that has a size exactly k. And yeah, this is why we don't lose anything here. And we get the 6.35 approximation. Okay, so this concludes the part on the k-means problem. And now I'm going to talk about some future direction and the problems that I'm interested in working on. So I'm interested in working on new clustering problems. So one of them is hierarchical clustering, where we want to find a clustering with different levels of refinement. And you can see an example here, an example of hierarchical clustering. In hierarchical clustering, we don't know the number of the clusters that the solution should have. I mean, there's no fixed number of clusters that is required, and it will correspond. And this clustering will correspond to a tree like this. And it wasn't really even clear what the objective for this clustering should be. So the first objective was suggested for this clustering by Dasgupta in 2016. So there are still open problems on this clustering problem that ask like which clustering algorithm work well for this objective function, which one of them doesn't work well. And I'm also interested in working on,
What is the objective function?
It's related to this tree, so they have a weight, and then for each subtree they have a weight that they said the weight plus the distance between the points. It's kind of related to that.
But why can't you just ask for hierarchical k-means? You want simultaneously cluster for all possible values of k, isn't it? Doesn't make sense.
For all possible values of k?
Yeah,
so
it's
will
like
they
a
just
binary tree of k. I want 2.
No, but you don't necessarily want like 1 into 2 into
2,
4
3.
into 8. Maybe there is a natural structure that somehow like.
Yeah.
I see.
And then another problem that I'm interested in working on is a fair clustering. Yes.
One more question. So what is known? So this is a stock paper of or what? Yeah. So what is known for this problem?
So as I said, people are looking at the problem that which algorithm work well for this and then which don't. So there's this like single linkage algorithm and these algorithms that some of them are bottom up, some of them are top down algorithm. And people are just working on showing that this algorithm, they don't give good results. But then for some algorithm, it's not known if they work well or not. And fair clustering is when we want to find, we are given a set of points and they have colors. And now we want to find clusters that inside the cluster, the color are balanced. So we have the same number of red and blue points inside each cluster. And then some problems on this are how can we design a fair algorithm, so that an algorithm that finds this color balance clustering. Or one other problem is, can we find a representation of the data points so that any classic algorithm that we use and apply here will give us a color balance clustering. I'm also interested in working on fast algorithms for basic clustering problems. So really, right now, the issue is that the data sets, they got very large, and then the classic algorithm, they don't work well on this data. So the goal is to find an efficient algorithm that can be implemented in the distributed computation platforms and on cloud services. And there has been some work on K-center and K-means problem for finding fast algorithms. And of course, for basic problems of clustering, we already know good polynomial time algorithms. But how about the generalized facility location problem? For this problem, we don't even know a good polynomial time algorithms that give us some guarantee. So examples of generalized facility location problems are basic problems that are obtained, but if we have a basic clustering problem and we add some additional constraint to better model the problem that we are looking at. So for example, we allow outliers. So some clients might be left unclustered or unassigned. Or we use upper and lower bound constraints. So we say that if you open this facility, it has to serve this maximum number of clients or this minimum number of clients. So let me give you more details here. So for example, when we have, why do we want to allow outliers? So we know that the data sets, usually they contain noisy data. And then clustering objectives, they are really sensitive to noisy data. So what we want to do is that if you want to get a good clustering, we have to be able to ignore some of the data points and leave them. So we want to focus on the data points of interest. And one problem that wasn't really explored is the K-means problem with outlier. The only result came out for this problem very recently is a 53 approximation algorithm. And no true approximation is known for this problem. So some open problems are, can we get approximation for K-median problem with outlier, or better approximation for K-means problem with outlier? And we don't really even know if these problems are harder than the basic versions. So the question on the hardness is also open. And then,
like in this thread, like if I say that I only ask for 1 minus epsilon fraction of the points to be clustered, and I compare with the op which clusters every point. So can you improve dramatically these approximation factors? Like, it's not exactly same as outliers, but I'm saying you don't have to cluster all the points, you just cluster me 1 minus epsilon fraction.
yeah, and then your object, so the problem is that
I just want to compare against the LP for the entire.
I mean, you might get a, so the point is that if you have some points, just assume that you have all the points here and then there's one point very, very far. If you are allowed to not cluster that point, your cost can go down drastically.
I guess.
But you want to compare to the optimal that also clusters that one?
I mean,
So I interpret his question as, I don't care about just clustering the set of points I've seen. These points are actually coming from some data generating distribution, and I believe that there is some underlying multimodality to the distribution.
Okay.
And so I'm actually okay with just clustering a 1 minus epsilon fraction of the points to get a, and then sort of compare that with the op to maybe reason about what the data generating distribution may look like rather than just the set of points I have seen. Like that's one motivation for a question like that.
So now the question is, can we get better approximation?
or better
It's a strictly easier problem. So
Yeah.
But the thing is, when you say approximation, you really want to compare your solution toward opt.
Yeah, but opt, let's say, clusters all the points.
Okay, so your solution might be much better than that.
Yeah. So, okay. That was the point, whether it gives any improvements or.
Okay.
Potentially, you could get much better approximation
Yes.
factors. So anything like that, no?
I mean, the problem that I've seen usually compares your algorithm. I mean, the opt is also doing the same thing as you. So if you are allowed to not cluster some points, the opt is also allowed not to cluster. But what he's asking is that you are allowed, but the opt has to cluster everything. So kind of comparing two different things. So for that.
This is scheduling and other areas. It's called
Yeah,
resource
by
augmentation.
by
Yeah.
criteria approximation, it's all about that. So it's
Yeah, I mean,
just
anyway, I think it might be tangent. Yeah. And this is Krishnaswamy and Sheely's result recently, which is, I think it's not even published, right? Like this 53 approximation.
I think Shili has answered that too. Yeah. Yeah, it's very recent. Like,
Yeah.
I think it was October or November.
Yeah, I think it's.
Yeah. And then another constraint that we can add is the lower bound constraint. So there are motivation for adding this lower bound constraint. One comes from the anonymity perspective, where so Samarati suggested that and says that if we want each cluster to have a certain number of clients in it, then it would be harder to identify the original data. Or maybe we want to add the lower bound constraints because from the facility location perspective. So we say that this facility, it's infeasible or unprofitable to open this facility unless I know that it serves at least a certain minimum number of clients. And so some open problems are getting approximation algorithm for lower bounded k-median or k-means. No result is known for these two problems. And again, hardness of these two problems. And while I will like to continue working on clustering problems, I also like to explore other problems that come from modeling real-world problems. One such problem is resource management in large networks. That say we have tasks that require access to the various resources on the network, and each task yields some profit. The resources, they have some capacity, and we want to find the most profitable, feasible assignment of task. And also I was talking to Nikhil, and this is something that comes up in assigning tasks to the processing units when we are looking at the cloud computing. And so I have some initial results on this. It's called for a couple placement problem, and it was approximation algorithm. There's still room to do room for improvement for this problem, and even getting fast algorithm is open, and it's another problem that can be explored. So that's all I wanted to say. Thanks a lot for coming. Any questions?
So one is a minor one. So this is just the last one. So what separates this problem from just formulating it as a min-cost max flow kind of set tasks on one side, have resources, and put the capacities on appropriate edges, and sort of interpret the solution of a min-cost max flow as this allocation?
So the idea is that we have different resources. So what will happen is that, so you have a job, and then it requires access to, for example, storage resource or computational resource. So
multidimensional.
Yeah, so it's not just one dimension.
So the actual question I had was, in two of the follow-up works, I saw this come up in the balanced color clustering, as well as in the so you spoke about what is a good representation of, exactly. So can you say a little bit more what's...
So this is something that I saw in the NIPS, current NIPS, and someone worked on it. And so the idea here is that you want to find a representation of the data that any algorithm that you use will give you a balanced clustering. And a representation can be that instead of just telling the algorithm what your points are, what you're going to do is you first find a matching between red and blue points. Say you match this point to this point, this point to this point, this point to this point, and this one. Then you give for each matching, you give a point to the algorithm, and then ask the algorithm to cluster that. So now any algorithm that you apply, because each point is basically embedding one red and blue, any algorithm that you will use, that clustering would be color balance. So now the problem is like a representation side.
So can we do better than this, just pairing up?
I mean, of course, this was just one idea, but so now the problem is, what can we do? What are the possible things? Maybe you don't want a matching, you do go higher dimension, like you do 4 points and then you make something as a representative of these 4 points. Good question. Yeah.
So sometimes you may not exactly know what is the number of clusters that you want to get, but
Yeah.
you may have some kind of constraint on the number of data points that you want to put in the cluster. Say you open a facility, but you don't want to open a facility just for 2 clients,
Yeah.
but you want to have a fixed number
Yeah.
there, at least.
Exactly.
Is there any definition for this, or where would it
So
fall
this
in terms of
assume-
results?
Yeah, so what you mentioned is exactly kind of like lower bound.
Yeah, here. Next.
Yes. Lower bound facility location problem. So you want to open a facility, and when you open a facility, you have the constraint that this facility has to serve at least something. So for the facility location version that you pay an opening cost, something is known. I mean, I have a paper on that lower bounded facility location problem. And I also have a paper on lower bounded clustering problem, which is kind of similar to what you're saying. You just want cluster. And then the objectives that we look at, one of them is case center objective. So you want to minimize the maximum radius of the cluster. And one objective is you want to minimize the sum of the radius. So we have approximation algorithm for these cases.
And what happens if, by introducing this constraint that you want n points in one cluster, it may happen that the cluster becomes really not consistent? Like,
Yeah.
Is there any way how to integrate these two? And
To check the feasibility?
yeah.
Yeah, because you can just solve a flow problem. Because usually in the facility location problems, the assumption is that like you have polynomial number of clients and polynomial number of facilities, so you just put them in you make a network flow, and then you put a requirement that each of these has to serve at least certain number of clients. So if the flow exists, then you know that there exists some assignment that does this. Yeah, next question.
Yeah.
So I'm curious if the LP view to clustering can actually extend to soft clustering, where I'm not doing a deterministic allocation of clients to facilities, but it's actually a probabilistic allocation. And this comes up a lot in topic modeling and things like that. So you don't say like a word is deterministically associated with the topic. You instead say like, well, this word has some distribution over the set of k topics.
Okay.
So often you have these, or like these Gaussian mixture models and things like that. So you always have a soft notion of clustering that it's a, and then there are some works that do the equivalence between like a low variance limit of soft clustering, basically giving you back k-means and things like that. But I'm curious if have you ever thought about like the linear programming view sort of generalizing to give soft clustering?
No, I haven't really worked on this, like looking at it from this perspective that you just give a distribution of how your client should be assigned. I mean, it's a nice question.
I also wanted to follow up on Nikhil's question, right? I think you asked about like the stability of clustering, I guess. Like, or someone asked during the talk, but I'm curious to know, like, from the LP attack on the problem, how stable are we for, like, if we change the inputs like by a small bit, do the eventual clustering that we get stay relatively stable, or do they change like dramatically?
Worst case, it could change, right?
No, but there is a long line of work actually
Yeah.
in stable instances, and LP is quite stable in that, like Kosia and like
Yeah, if you
Irving
assume
Blum
that that optimum is stable or something
Yeah.
like that. So are you saying, does it always happen? Then I guess the answer would be no. You can always construct carefully something so that if you change it a little bit, then you end up finding a very different system.
But one line of work has been like if you sort of like ignore some small fraction of the input and your clusters, optimal clusters doesn't change much, then LPs give you a very good solution for that. Yes. Okay, let's kind of